Well, Tesla full self-driving version 11 was supposed to be the one we were all waiting for, but it looks like 10.11 is pretty amazing too. Let's take a look.
And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time.
Hey y'all, it's Dr. Know-It-All, so I don't have time to do this today. I'm actually skipping my workout. I never skip my workout. It's the only thing that keeps me sane in this world. But I'm skipping this for you because this is a big enough deal. And Andrej Karpathy, who is the lead of Tesla AI, has actually tweeted about this himself and replied to Hallmark's Catalog, who posted this. At least he was the one that posted it that I could find. So anyway, I'm going to do this entire thing uncut, just like raw and whatever. So if you hear ums, uhs, if I pause, etc., it's because I'm trying to remember how to make this all work. It's like, oh gosh. Anyway, it's also very early in the morning. So anyway, I'm going to start right off with the big thing because this is what Andrej Karpathy, actually, if we skip down here for just a moment, you can see that he actually talks about this. I'll make that a little bit smaller. But anyway, I want to talk about this first one. So full self-driving beta version 10.11 release notes. Again, I don't have this yet. I'm getting this off the interwebs. So I will do a full self-driving immediate test as soon as I have this, but I expect it'll be a day or two from the time that usually the release notes come out. Then it's a couple of days before I get it myself. Okay, so anyway, upgraded modeling of lane geometry from dense rasters, bag of points, to an autoregressive decoder that directly predicts and connects vector space lane point by point using a transformer neural network. This enables us to predict crossing lanes, allows computationally cheaper and less error-prone post-processing, and paves the way for predicting many other signals and their relationships jointly and end-to-end. And this is what Andrej Karpathy said, just FYI. Favorite item from the release notes, upgraded modeling of lane geometry from dense rasters, bag of points, to an autoregressive decoder that directly predicts and connects vector space lanes point by point using a transformer neural network. And then he goes on to say, let's make that a little bit smaller. This enables us to predict crossing lanes, allows computationally cheaper and less error-prone post-processing, and paves the way for predicting many other signals and their relationships jointly end-to-end. So this is all a quote from the release notes. Then he says, TLDR, or too long didn't read, a GPT-like transformer is now predicting the lanes and their connectivity. This direct-to-vector space framework allows predictions to be jointly coherent due to sequential conditioning and very easily used by planner due to sparsity. Excellent work from the team. Okay, so let's go back and take a look at this original point. There's a lot to unpack here. The absolute number one thing, and I will put a card to this at the end of the video and also immediately right up here, is that what we have is we're transferring from bag of points to vector space. I did a whole video on this, so please check that one out if you're not absolutely familiar with what that means yet. By the way, I've got a t-shirt. Starts with T, ends with A, has ESL in the middle, quote from Elon Musk from a month ago or so. Anyway, I don't think I've worn this t-shirt yet, so I thought you might enjoy that one. Anyway, So what we're going is bag of points means if you think of every pixel, so we've got an 8 camera view that's all stitched together, right? But just think about it as just a view like this, right? So you've got me. This will be the simpler way to think about it. You've got a picture, well, a video of me talking in the corner here, and there's a surfboard up here, there's some books over here, etc. So a bag of points is looking at every single pixel and saying person, not person, person, not person. So right, it's looking at my shirt, is it going, is that a person or not a person? It's looking at my face, person, not person, is looking at the surfboard, person, not person, etc. That's a bag of points, hugely computationally complex and difficult. And you can go in one frame, you can be like, oh, person. But then if I move over here, oh, I don't know if that's still a person or not, right? So the deal, and this is by no means easy, which is why Andrej Karpathy said congratulations to the team, is if you can change that into, think about it more like a 3D animation game in this place, what you have is a vector space object, which is person, which is this thing that is me. And if you can identify that and just follow it through the scene, instead of having I think this is recording at 1080p, so 1920 by 1080. So instead of having whatever that multiplies out to number of pixels, you've only got a couple of objects in the scene. You've got me, you've got maybe it says, oh, that's a surfboard. Maybe it says, oh, that's a bookshelf. Oh, that's a bookshelf, right? So you've got a half a dozen objects in the scene as opposed to a million plus pixels in the scene that it's calculating. This is the transformational, because it is a transformer. This is the transformational aspect of going into vector space. This is the crux of getting to full self-driving in my mind. And that, again, I talked about in that video. It's hugely, crushingly important to understand this. Once you have objects identified in a scene and it's a vector space thing, it's all just a video game. You're just playing, like you're not GPT-3, you're playing, what is it, GT? Anyway, you're just playing a game, a video game in the world, right? So you're just like walking out, people are coming into the scene and, in the video games, people are shooting at you and stuff, right? Hopefully that doesn't happen ever in reality. But anyway, you're just dealing with a bunch of stuff that's effectively a video game, and the rest of the pipeline downstream is relatively easy. So it's all about the vision. It's all about comprehending what's going on and changing from bag of points where you've got millions of individual points per frame that you've got to keep up with, massively computationally difficult and hard to do, to going to a sparse vector space, only a few objects. You've just got these vector objects in the scene. It just makes everything so much easier. It's insanely difficult to make that jump, but conceptually it's very simple. It's like, oh yeah, if we just go from all of these points to vector space, everything becomes really, really easy. It's just really, really, really hard to do that. Anyway, so they were doing that for things like pedestrians and other cars and stuff. But now what we're getting is vector space lanes point by point using a transformer neural network. So a transformer is a hugely important new type of neural network that's come out. It's interesting that Andrej Karpathy recently has been talking about that. I'm going to talk about that just a little bit more in just a minute anyway. But what this does now is it now makes lanes themselves. So especially crossing lanes, it looks like crossing lanes, computationally cheaper and less error prone post-processing. Again, like I said, when you move to sparse vector space as opposed to really, really dense raster space, you're moving into a place where you don't have to use as much post-processing and downstream computation. So all of that is great. But what that means is we're modeling now intersections, right? So when you come up on an intersection, it's not just a bag of points. It's not going like, oh my gosh, there's points everywhere. What the hell? Where are the lanes? Everything. It's modeling out these lanes more or less like a person would do. We see lane lines. And it is confusing sometimes, but most of the time you're like, oh, that's the place I need to turn because that's the proper trajectory into here. And even though there's a bunch of dotted lines and dashed lines everywhere, I pretty much understand where I'm supposed to go because I'm sort of abstracting that into a quasi vector space. That's what us human beings do. Okay, so anyway, it paves the way to be able to do all of this kind of stuff, less error-prone post-processing, predicting other signals and their relationships jointly end-to-end. So if we skip down here again to what Andrej Karpathy said, TLDR, GPT-like transformer. Okay, so GPT is generative pre-trained. GPT-3 is a massive thing that OpenAI has been working on. It's again, monstrously, I think 140 billion parameters in there, plus who knows how many hyperparameters. It's absolutely crazy to do. But Andrej has been talking, and it seems like he's been talking about this on purpose because they've been working on this, that if you throw a complex enough neural network at a problem, it will solve it. So GPT-3 or GPT-like transformer, and Andrej, I think he rewrote GPT-3 on his own over like a weekend or something like that. He's just that kind of a crazy person. Maybe it was GPT-2. But anyway, it's just he's kind of nutty about being able to do this kind of stuff. Like, talk about a genius. But anyway, using that transformer, in other words, using a generative pre-trained, using a pre-trained type of transformer and then fine-tuning it for these types of conditions allows them to overfit to certain conditions. So what we're looking at is a lane type condition. This indicates to me that there is also GPT-like transformers going on at other steps too, for like human beings and cars and other objects in the scene. And if that's the case, that's different. The last kind of big news we got about all this was like a HydraNet. That was back at AI Day, August of last year. So it's possible that they've changed the architecture significantly since that point, and it's using more like GPT-3 right now, or GPT. Anyway, GPT-3, interestingly enough, GPT was originally a language modeling system, but it turns out it's so powerful that you can model anything with it. And if that's the case, it looks like what they're doing is they're modeling visual systems with it, which is just astoundingly complicated and super, super cool. So anyway, that's what we're looking at here. So, so we've got jointly coherent. Jointly coherent means that that we've got the ability to connect up pieces, right? So again, if you have a raster type of system, you may see a piece of a lane over here and a piece of a lane over here, but you don't know how to connect them together. When you're able to move into vector space, you can make predictions about how those things connect together. Remember, the real world is super messy, so this is really impressive that they're able to do that. And sequential conditioning, I assume that means in the training aspect of it, that they're sequentially conditioning all of these things on progressive frames through a video, and of course very easily used by the planner due to sparsity. That is the absolute crux of this video. That's the TLDW of this video, is sparsity rules. If you can move from a dense bag of points, all of the pixels that you have to deal with, down to just dealing with a few dozen or even 100 vector objects in a scene, everything becomes much, much easier. So this is hugely important. There's other really important stuff in this release notes too. So let's move on. Anyway, I just wanted to touch on that first, obviously because it's number one and they usually front load the really, really big thing, but also because Andrej Karpathy, replying to Holmar's catalog, talked about that and said it was his favorite part. So I think it's really important to talk about that. All right, so next one, use more accurate predictions of where vehicles are turning or merging to reduce unnecessary slowdowns for vehicles that will not cross our path. This is something that is really important from a user aspect. A lot of times what will happen is a car will be exiting a lane or something like that, or crossing in front of you. You as a human are like, yeah, they're far enough in front that we don't have to worry about it, but the autopilot will go, and brake for a person who's exiting a lane or something. So I will be testing that out as it doesn't say how this is being done, but anyway, more accurate predictions will be good because it will reduce what's called jerk, which is the third. There's distance. First derivative is velocity. Yes. Second derivative is acceleration. Third derivative is jerk. So anyway, the third derivative of distance, right? So distance over time. Anyway, so it will cause it to be more comfortable. The car won't jerk. My wife won't go crazy. She hates it when it does that. She's like, why did it just brake? And I'm like, it's having problems figuring this stuff out. Anyway, that should definitely help. So unnecessary slowdowns, always getting rid of those are great. Next one is improved right-of-way understanding if the map is inaccurate or the car cannot follow the navigation. In particular, modeling intersection extents is now entirely based on network predictions and no longer uses map-based heuristics. So again, that goes back up to this first thing about modeling intersections. So what we've got is, so it's using network predictions now as opposed to using a low resolution GPS type map or some sort of map, Google Maps or whatever that they're using currently. I think it's still Google Maps, but anyway, or maybe it's, gosh, I don't know. Whatever map system they're using, it's not using that anymore. What it's doing is that it's actually modeling this stuff out internally, and that actually really, really matters. So anyway, and also if the map is inaccurate. So but previously, I guess if the low resolution map was inaccurate, then the autopilot system would get confused about what was going on. And now it's just like, I'm just going to do it myself, probably because they've got this computationally so much more efficient. Intersections are incredibly, incredibly dense and complicated things for this entire system to work with. Interestingly enough, we just drove 20 hours back and forth to see my parents using full self-driving and everything. It's great on the highway, great on roads, great on back roads. Intersections are the place where it still has trouble. So this is really good to see that they're improving modeling of intersections and making this all significantly better and not depending on, all of these pre-done maps, making it essentially just doing it live as it's going, right? All right. So the next one is improved precision of VRU, which is vulnerable road user, like a cyclist, a pedestrian, somebody in a wheelchair, those kinds of things. Improve the precision of VRU detections by 44.9%. That is huge. A 5% improvement is impressive. 44.9% is insane. Dramatically reducing spurious false positives, pedestrians and bicycles, especially around tar seams, skid marks, and raindrops. I did an interview with James JOWUA. He talked about this, actually not with me specifically, but with Dave Lee. He talked about this specifically about tar marks and things like that. So that would be like if you're repairing a road and you put down tar marks. Apparently that causes the car to phantom see human beings or other types of things, or cyclists or something like that in the road, and skid marks and raindrops all of that kind of stuff can lead to the car seeing a person and immediately braking, because that's an incredibly emergent situation. So that is a huge amount. If you have a false positive, that's where you get this insane braking. It's like, you're driving highway speed and all of a sudden the car just slows way down because it's like, person in the highway, right? So anyway, this was accomplished by increasing the data size of the next gen auto labeler, training network parameters that were previously frozen, and modifying the network loss functions. We find that this decreases the incidence of VRU-related false slowdowns. Okay, so anyway, data size, right? Data is king. They increased the amount of situations of false positives by grabbing, I guess, tar marks, rain, etc., things like that. Then they worked with the auto labeler, which labels all of this stuff by itself to say, hey, this is all false stuff. Don't go for it. Don't stop here. And then training network parameters that were previously frozen. So that's interesting. So it sounds like what they did was they said these parameters are necessary to hold on to. Maybe something like if you even think you see a pedestrian and it's got a 0.05 chance of happening, stop anyway. So maybe they're like allowing that stuff to be tuned now, and modifying the network loss functions, which means so maybe what it's doing is increasing false positive punishment, right? If it thinks it sees a VRU and it doesn't actually see that, it increases that punishment. So that's the loss function. It's like bad AI, right? So anyway, we find that this decreases the incidence of VRU related false slowdowns. 44.9%, again, dramatic. This should have a real world effect. You should notice that when you're driving, there shouldn't be nearly as many phantom braking issues or anything like that. All right, so moving on to the next one. Reduced predicted velocity error of very close by motorcycles, scooters, wheelchairs, and pedestrians by 63.6%. Again, massive, massive reductions. To do this, we introduced a new data set of simulated adversarial, high-speed VRU interactions. This update improves autopilot control around fast-moving and cutting-in VRUs. So here we have simulated, interestingly enough, adversarial high-speed VRU interactions. So I think what we're talking about here is they're talking about like a pedestrian, a cyclist, a wheelchair, a scooter, something like that, a person who goes rapidly into your lane. So they're making a high-speed, perpendicular, not parallel. They're going perpendicular to you at high speed, which could be a cyclist that's making a lane change. It could be a pedestrian, somebody in a wheelchair, somebody in a scooter who cuts out from between cars or across an intersection against a light, something like that. So anyway, all of this allows them using simulation, so they're not having to do this with actual real human beings, because again, you don't want to put people in danger. So this goes back to the simulation episode I did on AI Day. Excuse me. But I think it's important to understand that they're using simulation here because this is an incredibly dangerous situation. You don't want to actually put people out there going at high speeds, perpendicular to your path and making the car have to deal with that in the real world because somebody could get hurt. So it's very important that we understand that that's what's going on here. So anyway, I think that it's hugely important. Notice 63.6% again. That is massive, massive improvements. These are not small improvements. The 10.10.12 or 10.10.2 video that I did, I said small improvements. This is looking like really, really huge improvements. Again, we haven't gotten to the one stack to rule them all yet with version 11, but this is going to make a big difference in real world stuff. All right, next one. Improved creeping profile with higher jerk when creeping starts and ends. So jerk, remember, again, third derivative of distance, right? We have velocity is the first derivative, acceleration is the second derivative, jerk is the third derivative. What that means is that kind of motion that you get when starting and stopping. This actually will help. It's interesting. Higher jerk actually is a good thing in this case. You want the car to slow down quickly and you want it to speed up quickly. The creeping behavior right now is very... oh gosh, what would you say? It's very unassuming. It's like, oh, please don't worry about me. And it creeps forward and it starts, slowly. You want a car to be assertive when it comes to a stop and when it starts up. So it will be very good when it creeps a little more jerkily. Under most circumstances, you don't want jerk. In this case, you actually do want jerk. Next one, improved control for nearby obstacles by predicting continuous distance to static geometry with the general static obstacle network. So nearby obstacles, that would be the thing that matters. So things like garbage cans, cars, mailboxes, I guess, tree branches sticking in the road, garbage bags that somebody's thrown out, things like that. So it's going to be better at predicting as you move past this, the continuous distance. So rather than frame by frame going like, how far away is that? It's actually going to be modeling out, if this is a static object and I'm moving at 40 kilometers an hour, how is this going to be moving relative to me? So it's going to be improving that. Doesn't say by how much, but that's very cool that it's doing that. Okay, and then kind of connected to that is the reduced vehicle parked attribute error rate by 17% achieved by increasing the dataset size by 14%, also improved brake light accuracy. So that's important as well. Brake light accuracy, like when you see it, the lights will go on for the brakes. The car's in front of you, you can visualize that. And if you look, sometimes you'll see the brake lights flicker and stuff like that. So the car was not doing the best job of visualizing that. It'll be great if that accuracy is better. Vehicle parked attribute is really important. That means it's saying like, is this car just stopped at a red light or sitting there, or is the car actually parked, right? And it's improved that by 17% by using a bigger data set size. So anyway, so that should be a really, really big improvement as well. Again, 17% better detection of parked cars. Good thing. I hope it's doing it both directions. Also noting when cars are not parked, because sometimes my car will attempt to pull out around people who are waiting at a light or something. And that's not good behavior either, right? You don't want it pulling into the opposing traffic lane because it thinks the cars are parked. So it should hopefully understand better between the two. Next one, improved clear-to-go scenario velocity error by 5% and highway scenario velocity error by 10%, achieved by tuning loss function targeted at improving performance in difficult scenarios. So clear-to-go scenario means, let's take an unprotected left turn. You're here, there's a high-velocity road like a highway or a 45, 50 mile an hour speed limit road by you, and it's going, again, perpendicular to you. And so the car has to predict when it can actually make a turn, right or left-hand turn, unprotected into this area. And any kind of improvement in this will be really helpful, because sometimes, again, it just kind of sits there and it doesn't go, even though you as a human are like, you definitely can go right now. So anyway, it should have the error should be reduced, and especially on the highways, which is like even higher velocity, has a 10% better clear-to-go situational awareness. So these are relatively small, but again, it should help. Even if it's, what is that? 1 out of 10 times, 1 out of 20 times, yeah, that kind of thing. So on the highway, like 1 out of 10 times ish, it does better. So that's not a massive improvement, but it still should help, because there's a lot of situations where the car just sits there and you finally just have to like tap the accelerator and say like, hey, yo, you need to go now. So hopefully that will reduce that type of minimal interaction with the full self-driving. Okay, improved detection and control for open car doors. That's the thing that scares me, because the car always passes really close to parked cars. So hopefully it will be able to detect that easier and move out around cars that have open car doors. So that's a good thing as well. Improved smoothness through turns by using an optimization-based approach to decide which road lines are relevant for a car given lateral and longitudinal acceleration and jerk limits, as well as vehicle kinematics. Whew, that's a lot of stuff. Again, we don't have a statistic on this. I don't know how much improved smoothness, but basically what it's doing is it's optimizing things and taking account of jerk. Again, jerk is the thing we really don't want, which is that kind of jiggling motion, the third derivative of distance. So anyway, the optimization-based approach should basically say like, discount these lines, these road lines, discount cars or other objects that are not going to be interfering with you, making a turn, especially turns. Turns are a big place where we have a lot of jerk still in the full self-driving. This is really cool, both for what it's doing, but also for it indicating that the full self-driving has gotten good enough at this point that they're turning towards comfort of driver. When they're doing that, they've kind of already accomplished a lot of the steps. The safety steps are already being taken account of, and now it's like, how can we make this comfortable for the passengers in the car? So that's really cool, and that's very important. Anyway, lateral and longitudinal, so forward and backwards and, sideways and forward and backwards jerk. It doesn't want to be slowing down, speeding up, or turning and then jerking and jerking and jerking, which the car does sometimes. So all of that stuff is really, really important. Again, it doesn't say how much, but it has improved that. Improved stability of the full self-driving UI visualizations by optimizing the Ethernet data transfer pipeline by 50%. Interestingly, I didn't know, apparently they have an Ethernet data transfer pipeline internally in the hardware. So that's kind of cool. Anyway, we should see better visualizations. They shouldn't be quite as jerky. I think especially on the Model 3 and Model Y, older Model S's and X's. Hopefully the new one with the better graphics chips will do a better job in general, but this should improve things and make them a little bit smoother. And then finally, improved recall for vehicles directly behind EcoCar and improved precision for vehicle detection network. So this just means that it's remembering, essentially. It's like, is there a car behind me? Improved precision for vehicle detection network. So in other words, I think this is specifically for, I hope, this is speculation at this point because it doesn't say this, but I think what we're talking about here is if a car is behind you, it's remembering it's behind you and it's remembering how far away it is behind you. Remember, there's only a single camera behind you, so you can't do stereoscopic vision automatically, but you can use other things. You can use things like how far apart the headlights are, how big the car appears in the scene, things like that to give a sense of how far away a car is. This is important because you don't want to break so say you're on the highway, you're driving, full speed, and people start to slow down ahead of you. You don't want to wait till the last minute and slam the brakes on if a car is tailgating you, like they're riding your butt on the road. You want to slow down more slowly so that car doesn't rear end you. So I would imagine that's the kind of thing we're talking about here. Sorry, recall here in this situation is not recall in the sense of memory. It's the precision and recall thing. So recall is, I can never remember which one's the false negatives and which one's false positives. Precision, positive. I think false negatives is the recall. So what that means is that it's saying it's not getting as many false negatives about cars and something about the distance. Anyway, this one's a little bit difficult to parse because precision for vehicle detection network would be false positives. So anyway, I think it's just saying like it's doing a better job of detecting cars and keeping track of them behind you and possibly also around you as well. So I guess if we're seeing this, what we would get is less flicker and cars fading in and out, especially if they're hidden by other cars, things like that. But anyway, hopefully the upshot is what I'm talking about. It's taking better account of cars directly behind you and also remembering cars and doing a better job of detecting them around you as well. All right, that is a lot of stuff to go over. Again, I just had to do this all straight out because I've got to go on with my day. But I hope that this is helpful for all of you. This is a huge update. The last one, 10.10. Whatever, was a relatively small one where they just had to fix the problem with the coming to a complete stop at stop signs. This is a significant improvement. This is a significant update. I can't wait to get it and try it out. I'm gonna put it into these scenarios and see how it does. In the meantime, let me know what you think about all of these improvements. What is your favorite improvement? We all know what Andrej Karpathy's favorite improvement is. I would love to know what yours is. And, of course, in the meantime, don't forget to like this video if you enjoyed it and subscribe for more of this kind of content. As always, a huge shout out to my patrons on Patreon. I really appreciate everything you've done. I know I've been traveling recently. I appreciate your patience with me as I travel and move around and everything. And of course, if you want to join the team, definitely check out the link in the description. And of course, don't forget about the merch store. Got shirts like this, whole bunch of shirts, mugs, tumblers, etc. Just check it out. Link is in the description as well. And of course, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.